Okay, welcome back, everybody. Before I start to share my screen and open up a Julia session, I want to remind everybody of a problem that appeared in the beginning of class. It was a parameterized polynomial system with 27 solutions, which corresponded to this beautiful classical result in algebraic geometry. So the result is the generic cubic in three-dimensional space contains 27 lines. And so we cooked up a parameterized polynomial system which computes these 27 lines. This was one of our first computational classes where I was just kind of showing you generally what homotopy continuation in Julia could do. So I want to just go through how we constructed this system again. And today we will compute the monodromy of this problem. So a cubic looks like the variety cut out by a single polynomial, degree 3 and 3 variables, which generally looks like this. So I got a bunch of parameters for the coefficients. This is a sparse polynomial system, albeit not a square sparse polynomial system, because it's one equation, 3 variables. 20 parameters, I think, was around 20 parameters. So down here is the space of cubics. So I have coefficients, which are my parameters. And you give me one of those, means you've given me a cubic. And if you randomly give me one of those, that means with probability 1, you've given me a generic cubic in the sense of this result. And so I hope to find the 27 solutions, or the 27 lines, if you will, which are contained in that cubic space. So our solution space is the space of lines in a three-dimensional space. And you can think about that as, so here's a three-dimensional space. Give me a U, give me a V. And then this line is the image of t goes to U plus t. Sorry, give me V is this vector from, okay? How do I parameterize this line? Well, at t equals 0, I'm just going to be here. And at t equals 1, I'm going to be at U plus V. And so that's just the parameterization of a line. Okay, but this is 3 coordinates. This is 3 coordinates. Almost all lines are going to go through the xy plane. So might as well just do that. And the vector, almost all lines are not going to be parallel to the xy plane, so I can let this vector have a 1 in the last coordinate. So now almost all of my lines in three-dimensional space can be described by 4 complex numbers: U1, U2, V1, V2. I'll call this L of UV. Okay, so now L of UV, I guess the variety cut off by L of UV, lives inside the variety cut off by my cubic, if and only if when I actually do the composition. So somebody give me a cubic. The x is being replaced by u1 plus tv1. The y is being replaced by u2 plus tv2. The z is being replaced by t. And I do this composition, and I get a polynomial in T. And it has degree 3. Because if I compose a degree 3 polynomial in 3 variables with linear forms, I don't change the degree. Or you could also think about it as, well, let's write it down. 3 times t cubed. So this is my polynomial of degree 3. Stuff times t cubed plus stuff times t squared plus stuff times t plus stuff. The t values for when this is 0 are the intersection points of this line with the cubic. So if I want all the t values to give me 0, then I need this polynomial to be identically 0, which means I need f3, might as well just write it, f2, f1, and f0 to all be 0. That's 4 equations. We have 4 variables and 20 parameters. That's our parameterized polynomial system. Let's write it down in Julia. And let's solve. Okay. I am switching my screen sharing. Yes, I would love to keep these changes. Thank you. You get minimized. You get shared. Which one gets shared? Desktop 2 gets shared. Great. And we don't need you. Okay. This background should be becoming more and more interesting to you as the course goes on. Okay, here we go. So using homotopy continuation, what variables do we need? We are going to need an x, y, and z. We are going to need C. I want to write this, but the issue is that Julia indexes at 1. So I'm going to shift everything up by 1. So Cijk on Julia should be interpreted as Ci minus 1, Ci minus 1, J minus 1, K minus 1 on the blackboard. Okay. So I want to move this up. Okay. So now let's cook up a generic cubic. Well, it starts as 0. I'll say it again in a moment. So it's what I'm writing right now, this line. That the monomial corresponding to ijk, well, ij and k might individually be 0, right? So look on the board, you got like C0, 0, 0. Okay, that's a problem for Julia. That's going to be very annoying for us very quick. I don't want zeros in Julia because things get indexed by 1. So I've just shifted all of the indices in Julia up by 1. Okay. So you can see that the coefficient of x to the I, y to the j, z to the k here is actually Ci plus 1, j plus 1, k plus 1. And we're going to add that to the cubic. Okay. Awesome. Yeah. Okay, you happy? Okay, cool. So now what do we got to do? We need U1 and U2, V1 and V2. And we're gonna need like a placeholder for t value, I think. So now I'll say U is going to be like U1, U2, and 0. B is going to be like B1, B2, and 1. And L is going to be UI, so UI plus T times VI for I in 1 to 3. Okay, that's our line. Yeah. Okay. And now we've evaluated our cubic at this line. We have the coefficients of the cubic Cijk's appearing. We have the UIs and VIs appearing. And then we got this T, which is going to disappear in a second because we want the T value to not matter, right? Because we want the whole line to be contained in the cubic, not just some T values along the line to be contained in the cubic. So what we need to do is we got to get the coefficients. With respect to T. There they are. And those are our equations. Our parameter variables are U's and V's.
Maybe we should, write equations in the square brackets. The system takes expressions in square brackets.
Indeed. So EQS is already a vector of expressions. So I don't have to adjust it anymore. That's a good point. So there we go. We got a system of length 4, meaning 4 equations, 4 variables, and 64 parameters. Okay, we've really overkilled the parameters. Let's see, can we just get like the support coefficients of yeah, it's okay. Too many parameters never hurt anybody. They're not involved. Okay. Okay, monodromy solve is a hard-coded algorithm in homotopy continuation.jl. It really is indeed one of the fastest ways to solve a polynomial system. But as we know, it requires that this incidence variety cut out by the parameterized polynomial system is irreducible. Otherwise, we might not get all the solutions. Fact, for this, it's irreducible. Okay, and if you want to like be able to prove varieties are really irreducible super fast, take an algebraic geometry class. Otherwise, just trust in the literature or talk to me. So let's solve. And now we wait as we do. So what's this going to do? So it's going to pick a line first and find a cubic that contains it. It's going to do that automatically. That's because if I replace all the U's and V's in here, i.e. I choose a line, finding C's, i.e. finding a cubic, which makes this equation true, is a linear algebra problem. It's easy to choose a solution and find parameters for which that's a solution. Okay. And after it's done that, then it has a generic parameter and it has a single solution associated with that parameter. So it has all it needs to do to start the monodromy solve algorithm. It starts taking random loops that it constructs by triangles in the parameter space. And it doesn't just shoot around that first start solution. It does something smarter than that. Kind of does what Alex and Kate suggested, which is like, use the ones you've already found. And indeed, it does that. But then when does it stop? It stops as soon as it introduces 5 new loops, which don't contribute to finding more solutions. That's pretty conservative. But yeah, so that's what it does. So when it does this whole story, it keeps track of how many points it had to shoot around the loops. So in total, it had to shoot around like 189. But keep in mind that like 135 of those were just double checking that it had found all of them. At some point, it stopped finding new solutions because it had all 27 and it had to do like 135 extra loops to like double check this. If you already know the number of solutions, then you can just use that and put that in, and it'll stop as soon as it finds that many. Right? Why not? Like, you already know the answer. Why are you trying to find more solutions if you've already found 27? And there you go, 47 solutions. 47 points that had to go around in loops. Right? So that number 47 is measuring how difficult it was to solve. And do total degree of f. Does this work? No. All right, we can just do it.
If you didn't put in 27,
Sorry?
how did it stop? Or was stopping writing?
That it chose 5 new loops,
Oh, yeah.
which
Okay.
didn't produce any progress.
No.
Yeah. Okay, so all of these polynomials have degree 4. So no, sorry, they're degree 3 in the variables. They're all degree 3 in the variables. So we have 3 to the 4th. Great. 81 is the Bezout count. Okay. So instead of tracking 81 paths, this only had to track 49 paths. Okay. And we showed that in general, we kind of expect something around proportional to this. Okay. And that's if it was doing it the kind of silly way. So you would expect that if it has some upgraded ideas, then we don't need as many. Okay. Okay, cool. Here's something fun. So it can keep track of all the permutations. So in total, it ran over 7 different loops, 5 of which were just like sanity checks, basically. It really only needed 2 loops. And the columns of this 27 by 7 matrix are the one-line notations for the permutations induced by those loops. So for example, for the first loop, the first solution goes to the second goes to the third, and the third goes to the first. So it's got that 3 cycle in there. The 4th solution goes to the 8th, the 5th to the 10th, the 6th to the 12th, 7th to the 13th, okay. So that's how we read this. Now that's a matrix of numbers. That's not, I mean, it's fine. Like, we could write this down and we could try to do some like group theory. We don't want to do this by hand. We're hanging out an S27, which has size. I mean, we're really not gonna have a fun time. It's such a big number. The computer doesn't even want to say it. I have to do factorial big 27, everybody. Okay, so that's the order of S27. Okay, it's a huge number. You don't want to do any of this stuff by hand. So we got to figure out how to get these columns into like some sort of like group theory software so we can start asking questions about it. GAP is a very popular piece of software for studying groups. It has functionality to study permutation groups, and it is easily used in Julia through the system Oscar. Oscar is a computer algebra system which combines several well-known pieces of software, in particular GAP for group theory, Singular for algebraic geometry and commutative algebra, and Polymake for polyhedral geometry, matroids, toric geometry, stuff like this. And it's all wrapped together into this Julia package called Oscar, which is meant to be easily interoperable between all these cornerstone systems. So I could take a polytope and compute its automorphism, blah, blah, blah. Okay. So it's going to take a little bit to load, especially since I have Julia running.
Can you directly use GAP instead of through Oscar?
So GAP has a Julia package called like gap.jl. But that is to do the piping between GAP and Julia, whereas Oscar is really intended to make that easy for the user after the fact. and have it talk nicely between the other Oscar objects, like ideals and polytopes and matroids and varieties and all of that.
So always using through Oscar is advisable.
I do that. And I spend a lot of time doing these things. So to whatever degree that gives you confidence in my choice, I use gap exclusively through Oscar. If I had to do something perhaps like really, I mean, even if it was performance based, I would still like do it through Oscar. Because it's not like Oscar slowing down the computation at all, except in the sense of what you just saw, the using Oscar. Like you're gonna pay that price at the onset of your computation. Maybe it's a couple minutes. But still the hardcore computations are driven by the engine of gap. Right? It's not like these algorithms are re-implemented in Julia in some slower way or anything like that. So I think even if I was doing something where I really cared about performance and some large computation that goes over like the course of a month or something, I would still use it through Oscar. Okay. Great. So let's get these permutations each as a one-line notation. So the permutations of this monodromy solve story, but I want the columns. So I don't care what goes in the first. I don't care the I value of the xij, but I do want to fix the second one. So I think I said I had 7, right? Great. So here's one permutation as just a vector of integers, which isn't like really a permutation yet. It's just a vector of integers. We're interpreting it as a permutation. So if I want Oscar perms, I just want the perm. Oh, sorry. Oscar really wants me to fix an ambient group. Okay, so there's my symmetric group. And now my Oscar perms. Perm. Okay, so I gotta tell it, okay, it lives in the symmetric group on 27 things. Because in general, if I just, yeah, that should be implied anyway. I don't know. That's the syntax for today. There you go. Cool. There they are. So now, well, let's construct the group. So it's a subgroup of G generated by these Oscar permutations. Now, subgroup returns 2 things. It returns the group, but then it returns some inclusion homomorphism into the ambient group. We ignore that. And you can ignore that using this underscore. I just wanted to assign H. So I can ask for like the generators of H, and like there they are. Those are the ones I gave. Okay. Okay, so Taylor prompts you that monodromy solving only works if the monodromy group is transitive. So even if we didn't find enough permutations to generate the true monodromy group, by definition of us, like as a consequence of us finding all 27 solutions, we should have found permutations which form a transitive subgroup of the monodromy group. And so we can ask whether or not it's a transitive. Okay. We can ask if it's primitive. Yeah, it's primitive. Right. So what does that mean? There is no way to factor this branched cover of degree 27 because it has a primitive monodromy group. Okay. So now let's ask how big it is. That's pretty small. Oops. Oh, yeah. Okay. E to the next 24 here. By like 24 digits. Less than 24 digits, but yeah, so very, very small. Okay. Okay, and we can even ask Gap to describe it. Great, so that is a semi-direct product of the orthogonal group of either 3x3 over F5 or 5x5 over F3. Semi-direct with the cyclic group of order 2. Okay, blah, 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 blah. Who knows? Okay. So now I'm going to tell you what it really is, what this group really is. I told you that these groups are as big as possible, right? Subject to like you finding the obstructions. So I'm going to tell you what the obstructions are to permutations for the 27 lines. Okay. Okay, so I have some cubic here. I'm very bad at drawing cubics, I apologize. That's a cubic. And I have some lines. So these are lines on a surface. So it's possible that they don't intersect. Right? For example, if you think about like this like quadric surface, you can think about two lines that are skew on it. Okay. But maybe they do intersect. It also seems possible that they do intersect. Like if I have lines on a surface, I'm pretty agnostic about whether or not I should expect them to intersect. Okay. All right, so let's say L1 here and L2 intersect, but L3 intersects neither of them. Okay. Now I ask you, with this information in mind, so suppose that I found 3 lines, 2 of which intersect and 1 which doesn't intersect either. Is the monodromy group the full symmetric? Well, it should take pairs of intersecting lines to pairs of intersecting lines. Because if I wiggle the cubic around a little bit, they're not going to not intersect, right? So intersecting is an open condition here. Sorry, closed condition here. Okay. And so there does not exist a G in the monodromy group such that G acting on unordered pairs of lines sends the lines 1, 2 to the lines 1, 3. Because this permutation is induced by a continuous transformation of this problem. Right, and as I continuously move my cubic in some loop in the space of qubits, L1 and L2, along the way, they have to stay the same. Okay. Great, so this is an obstruction immediately to the monodromy group being S27. Okay, and I want to now summarize kind of all the obstructions which occur in this fashion. Okay, so how do I do that? Well, I take my 27 solutions and I think about them as the 27 points in some graph. And then I draw a line, an edge, between any pair of lines that intersect. So in this case, 1 and 2 intersect, but 1 and 3 don't. Maybe 1 and 4 do, and 26 and 4 do, and maybe 5 and 5 do. And you can cook up this graph. In fact, you have all the information because you have a collection of 27 lines here. So as long as you know how to check whether or not 2 lines in 3-dimensional space intersect, you could actually cook up this graph yourself. Okay. So this is a graph on 27 vertices, some number of lines, and looks like this. There you go. You can look at the screen if you're in class. So it looks like that.
They're like circulant,
Huh?
circulant.
No, it's not circulant graph. More interesting than that. It's called the Schauffele graph.
Mhm.
And if G is in the monodromy group, then G must respect this graph. Sends edges to edges. In other words, G is a subgroup of the automorphism group of the Schauffele. So that's another geometric obstruction that you could see. So if your solutions to your polynomial system have some geometric interpretation, in this case, they're lines, you want to think about how those geometric objects could be related, which would produce some sort of obstruction to how they can permute. Okay, so this is another way other than decomposability. This is not decomposability because we've seen that this monodromy group is imprimitive. This is a different obstruction. Okay, and people think about graphs much bigger than those on 27 vertices, so you can compute this group. And you can check that it has order 51,840, which means that this containment is inequality. Okay. Depending on what else your background is, this is the Boyle group of E6. Okay, any questions? Okay, so let's jump back to Julia. I'll show you a couple more, we'll do a couple more monodromy group computations, and then we'll call it. Here, let's do like A1 times X plus A2 times Y plus A3 times X squared times Y plus A4 times X times Y squared. Okay, so this is a sparse polynomial system. Second one, I'll just use B's. Okay. Okay, that's my system. Okay. If you had to draw these monomials, what shape would you be looking at?
Quadratic.
Hmm?
Quadratic.
A quartic.
Quadratic. Degree 2, degree 3.
So I'm looking in the exponent space, right? So this is 4 monomials. I'm gonna draw 4 dots. What do those dots look like?
Oh,
Say again, Kate? Oh yeah, it's a diamond. It's a diamond. It's like that. Okay. Okay. Any ideas of the monodromy group off the top of your heads? I don't know. Let's see. Oh, how about this? Any ideas how many solutions? Might do this volume computation in their head. No, let's see. Okay, let's just solve it. Look, if we solve this, then we've actually computed the mixed volume using monodromy. Is it faster? Who knows? Okay, now let's track the permutations. Okay. So the first loop we used was actually the identity, so that didn't help us at all in our monodromy computation. The next one swapped 1 and 2, and it swapped 4 and 3. The next one, sent 1 to 3, 3 to 4, 4 to 2, and 2 to 1. So that's a 4 cycle. Okay, great. Okay. So we are looking for the subgroup of the symmetric group on 4 elements, given by permutations. I should probably have it be the same symmetric group, I guess. Subgroup of term of G P or P in closed everything. Close, close, close. No. There you go. Okay. So order 8. Okay. There they are.
D4.
Let's ask. Yeah, they call it D8.
Yeah.
All right. We can ask for any blocks which might be respected. Let's first check sorry. It's not primitive, which means it's imprimitive, which means it has a non-trivial block system. Yeah, and so it's a wreath product. So it ends up being a wreath product, right? It's the same one as D8 as before. But here, the representatives of the blocks are solution 1 and 4. So 1 and 2 stick together and 3 and 4 stick together, right? So if you wrote down all of the permutations of this, 1 and 2 stick together, 3 and 4 stick together, you'd be seeing all those permutations. Okay. Okay. So on your homework, you're expected to find the branch locus of a branched cover onto the line. From your first homework, you know this is just a finite collection of points. You're supposed to compute the fiber of this branched cover over some regular value. I think I said 0 is a regular value. And label those solutions however you want. And then I want you to do loops around all the points in the branch locus and get the permutations. Okay, so I think you're gonna end up getting like maybe 3 permutations, maybe 4. 4 permutations, I think. Okay. And yeah, great. And then finally, you'll take those 4 permutations and you'll ask yourselves what group is generated by it. And you'll save yourself a lot of time if you just plug them into GAP through Oscar. So that's my hint. And then you have to tell me whether or not it's in primitive, whether or not monodromy solving would work. And those can be checked by just is primitive and is transitive. So, but feel free to work together. I encourage you to work together. Any questions about the coding? Any questions about the theory before we move on to our next section? Okay. The next section is all about a very particular type of branched cover. It's the branched cover you get when somebody gives you a variety and asks you to slice it with a bunch of hyperplanes until you get finitely many points. Okay, so there are the parameters. The parameter space is the space of linear spaces you're slicing with. And computing a fiber equates to computing a so-called witness set. We'll talk about monodromy groups of these branch covers. We'll talk about why monodromy solving is so wonderful for these branch covers, because there is a stopping criterion called the trace test. we'll talk about then how to use these fibers, these witness sets, to do essentially all the kinds of computations you'd like to do when you're thinking about variety. So that includes variety containment, sampling from the variety, sampling points from the real locus, like all of this stuff. Yeah, and that's the class for today, and I will see you next week for witness sets. Thanks.